I hope you're all having a great day. I'm Mr. Ish. Thank you for joining me for this video where we are looking at this single arch of cycloid and the area below it. We know the area is 3 pi r square. The significance of that is it represents 3 times the rolling area of a circle. 3 times the rolling area of a circle is equal to 1 arch of the cycloid. You know that circle has a certain perimeter, a point on that perimeter or circumference of that circle. As you rotate and translate that circle, it traces a curve which is your arch of cycloid. But if you do 3 times that rolling circle, you're generating an area equivalent to a single arch of this cycloid. A point on this arch P has an x and a y value which generates your, by means of the derivation process, your parametric equations, with theta being your parameter. It could be t, it could be theta, anyhow. How can you go about showing that this area is indeed 3 pi r square? That is our role and our goal for this video. 3 pi r square, the area of the arch of that cycloid, below the arch and above your axis. You look everything here with regards to this setup. Area of that arch from A to B, you have y and dx. In this representation, you're looking at a certain range here. Your value is between B and A. But when you're looking at everything here with regards to parametric equations, where you have an equation with regards to x and an equation with regards to y, with each of these having a parameter come into play, then you're looking at everything in this format. You're either looking at a g function and multiply by the derivative of the f function. Here we're looking at t's, but these t's could easily be thetas. Or you're looking at the f function times the derivative of the g function. But what's f and what's g and all of that? Well, in one instance, x can be your f function with regards to the theta or the t parameter, and your y would be your g function. In another instance, you can do x is equal to your g function and y can be your f function. Either or, it doesn't matter. But you see how the theta or your t parameter falls between your range alpha to beta in this situation, or beta to alpha here in this situation. All of this is just showing the general premise or the framework as to how this is handled, this type of integral format. And this type of integral format is only being brought into this picture simply because we're looking at something which involved parametric equations. It can seemingly appear as technical at first, but trust me, it isn't, because when you look at everything in a simplified manner, which is what I'm showing you, it will all make sense. When you're looking here at this representation, you know you're looking from 0 to 2 pi r, but when you're looking at everything with regards to your theta parameter, you're really looking from 0 to 2 pi in terms of your theta angle. Your area integral becomes basically 0 up to 2 pi, but you have a y and a dx. Remember, normally when you're doing area below curve, you'll have an f of x here with regards to your x-axis calculations and dx. When you're doing with regards to dy, you'll bring an x equals equation. All of that, those general principles are still true, but here we're looking at it in this form. Your y is this, your dx is that, but dx is the derivative of that. You're basically just doing a polynomial substitution, but you're substituting more than what you would normally be used to. This y here is this r times 1 minus cosine theta. It could very well have been your f of t, and then this can be your g of t, or this can be your f of t and that can be your g of t, like how I had earlier. Anyhow, here's my y. What's dx? Dx is the derivative of x. If x is this, the dx is the derivative of that, which is 1 minus cosine theta. The derivative of this x is what we're talking about. That equation is this with regards to d theta, and now suddenly our equation has come into play, our area integral. You see these r's bring about. You're looking at r square 0 to 2 pi, and all you're doing is this. Multiply these two. What do you get? 1 minus 2 cosine theta plus cosine square theta d theta. That's what you have. This cosine square theta is very well handled by a power reducing identity, or some people call it the half angle. I like to call it power reducing. You're looking at 1 plus cosine 2 theta over 2. You would bring this right over here. I'll erase this part right here so we can continue with everything over here. Our area integral now is r square from 0 to 2 pi. All of this 1 minus 2 cosine theta plus 1 plus cosine 2 theta over 2 d theta. But you see, this is a denominator too, these are not. Multiply this and bring a common denominator. When you do this common denominator, you'll have a 2 over here. Here you'll generate a 4. And then this 2 will end up representing the denominator of this entire expression. But if you want to be good, you can bring it out here and eliminate the need of having a long denominator right here. And what you see over there is good. You can then simplify it. A is equal to r square over 2, and then you have 0 to 2 pi, 2 plus 1 is a 3, minus 4 cosine theta, and then you have plus cosine 2 theta d theta. That's what we have. Everything here is easy to handle except for this, because this is still a composite. It would have to go through another round of polynomial substitution. But you can do a little bit of a shortcut here. If you do a is equal to r square over 2 and separate these into their independent integrals, you're doing 3 minus 4 cosine theta, all of this with respect to d theta, plus now another round here, r square over 2, you have 2 pi 0 and then cosine 2 theta with respect to d theta. If you were to integrate this, you'd bring in the sign antiderivative by means of the polynomial substitution. Whatever modifications would occur to this r square over 2 and the limits, all of this will zero out, because when you do your antiderivative, the sign will get hit with 0 and a 4 pi and will be a 0. All of that is 0 and you don't have to look at it any further. Everything here with regards to your area integral boils down to just this part, and I'm just removing this now for you because we don't need to worry about it. This part right here would have zeroed out, and this is what we have, and I'm cleaning it up for you. We have 3 minus 4 cosine theta d theta with regards to r square over 2 and 0 to 2 pi. The antiderivative of 3 is a 3 theta. You have an r square over 2 sitting outside. The antiderivative of 4 cosine theta minus 4 cosine theta would be a minus 4 sine theta. You're looking at everything from 2 pi to 0, but think about it, you can cut this away because the 2 pi and a 0 coming out, in terms of sign, is 0. The only thing which really remains is just a 3 theta. All that remains is a 3 theta with a 2 pi is 0, and then you have an r square over 2 sitting outside. The 0 is meaningless, you just put the 2 pi. You're having a 3 times a 2 pi times r square over 2. When you simplify all of this, you're having here a 3 pi r square, which confirms exactly what we wanted. The area under the arch of cycloid is indeed shown to be 3 pi r square by means of the procedure that I've shown you. It's not hard by any means, but this right here represents a representation for what you want to use, y dx, your y parametric equation and the derivative of the x parametric equation coming into play. As you've seen the entire process, again, the significance, 3 times the area of that rolling circle, or as some would say, 3 times the rolling area of that circle is equal to the area of one arch of a cycloid. Thank you for watching this video. Have a good day.